Hello again, my physics students. This is Mrs. Buchanan, and this is flip video number 7. We will continue our discussion of Newton's second law of motion, force and acceleration. Let's revisit our big idea. An object accelerates when a net force acts on it. In this video, we will be covering two learning objectives. Describe the relationship between system and environment, and contrast contact force and long-range force. You might expect a skydiver to plummet to Earth in a rapid, uncontrolled descent. Yet a group of skydivers can perform beautiful maneuvers as they drop toward Earth at high speeds. How do the skydivers control their velocities? We have discussed acceleration and how it describes a change in velocity of an object. Velocity, in turn, describes a change in the object's position. But what causes acceleration in the first place? In other words, why do things move? What is the cause of motion? The answer was given by our good fellow Sir Isaac Newton more than 300 years ago. He explained the way in which forces, pushes, and pulls influence motion. Newton summed up his explanations in our 3 clear and concise laws, one of which we've already covered. These laws explain what and how much is needed to make an object move. They also explain what happens when a moving object crashes into something. For example, Newton's laws explain why skydivers fall rapidly downward when they first leap from a plane. The laws also explain why after a time the divers continue their fall at a rapid but steady speed. Skydivers understand, and you will too, how changing the position of their arms and legs changes their motion, allowing them the freedom to perform extraordinary feats in the sky. Push your book slowly across your table, and then fasten a string to the book and pull it. By pushing or pulling the book, you are exerting a force on the book. An object that experiences a push or a pull has a force exerted on it. Notice that it is the object that is considered. The force is called the system. The world around the object that exerts forces on it is called the environment. You can push hard or gently, left or right, so force has both magnitude and direction. Force is a vector quantity. Contact versus long-range forces. There's two actual types of forces that are exerted by the environment on a system. The first one is a contact force. A contact force on an object acts on an object only by touching it. Either the table or your hands are probably touching your computer right now, exerting a contact force on it. Your hand and the table exert forces only when they touch your computer. The second kind of force is a long-range force. A long-range force is exerted without contact. If you ever played with magnets, you know they exert forces without touching. Suppose that you're holding a ball in your hand. The ball has a contact force exerted on it, the force of your hand. Now suppose that you let go of the ball. Although nothing is touching the ball, it moves because there is a long-range force, the force of gravity, acting on the ball. The force of gravity is an attractive force that exists between all objects. Forces have agents. Each force has a specific, identifiable, immediate cause called the agent. You should be able to name the agent of each force. For example, the force of the table or your hand on your computer. The agent can be animate, such as a person, or inanimate, such as a desk, floor, or a magnet. The agent for the force of gravity is Earth's mass. If you can't name an agent, the force doesn't exist. The first step in solving any problem is to create a pictorial model. To represent the forces on a book as it rests on a table, sketch the situation. Circle the system and identify every place where the system touches the environment. It is at these places that contact forces are exerted. Identify the contact forces. Then identify any long-range forces on the system. Now, once you have drawn that, next replace the object by a dot. That is, use the particle model, which means that you're going to use a dot to represent your object. Each force is represented by a blue arrow that points in the correct direction. The length of the arrow is proportional to the size of the force. The tail of the force vector is always on the particle, even when the force is a push. So you're going to label the force. For now, use the symbol F with a subscript to label and identify both the agent and the object on which the force is exerted. Now you're going to do some practice problems. Draw pictorial models for the following situations. Circle each system, draw the forces exerted on the system, name the agent for each force acting on the system. Number 1, a book held in your hand. Number 2, a book pushed across the desk by your hand. Number 3, a book pulled across the desk by a string. Number 4, a book on a desk when your hand is pushing down on it. And number 5, a ball just after the string that was holding it broke. So what you're going to do is you're doing something similar to a free body diagram. We call these a particle model. And so you're going to do the sketches of each of those 5 problems, and then you're going to do the labeling as I previously stated. If you need to listen to the video again, I would strongly suggest it. Thank you very much.